Imagine accelerating so fast that the stars themselves begin to blur into streaks of light. The entire galaxy shrinks ahead of you. Time slows to a crawl. A journey to the nearest star that should take 4 years suddenly takes only months from your perspective. This isn't science fiction, it's what would actually happen if you could approach the speed of light. Today we're diving into the physics, the possibilities, and the profound barriers that stand between us and the ultimate cosmic speed. If you're fascinated by humanity's quest to explore the cosmos and want to journey with me through the cutting edge of physics and space exploration, make sure to subscribe to this channel, give a thumbs up. And one quick question: if parallel universes are real, what's the most important message you'd want to send to other versions of yourself? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. To understand whether humans will ever reach light speed, we first need to grasp what light speed actually is and why it's so special. Light travels at approximately 299,792.458 kilometers per second in a vacuum. That's about 1 billion kilometers per hour. At this speed, you could circle Earth's equator 7.5 times in a single second. You could reach the Moon in 1.3 seconds, Mars in about 3 minutes when it's closest to Earth, and the Sun in 8 minutes and 20 seconds. But light speed isn't just about light. It's the universe's fundamental speed limit, the maximum rate at which any information, energy, or causal influence can propagate through space. This limit is built into the fabric of space-time itself, emerging from the deep structure of reality as described by Einstein's Special Relativity, published in 1905. The theory revealed something profound. Space and time aren't separate, absolute entities, but are interwoven into a four-dimensional fabric called space-time. The speed of light is actually misnamed. It should be called the speed of causality or the speed of space-time. Light happens to travel at this maximum speed because photons have no mass. Any massless particle or wave must travel at exactly this speed, never faster, never slower. It's not that light is special, it's that massless things naturally travel at space-time's maximum allowable speed. For objects with mass, the situation is radically different. Einstein's equations show that as an object accelerates, its relativistic mass increases. The faster you go, the more energy you need to accelerate further. This isn't like air resistance or friction that clever engineering might overcome. It's a fundamental property of space-time itself. As you approach light speed, the energy required approaches infinity. To accelerate even a single proton to exactly light speed would require infinite energy, which is obviously impossible. Let's put this in perspective with real numbers. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, can accelerate protons to 99.9999996% of light speed. That's 11 nines after the decimal point. These protons have been given enormous amounts of energy. Each one carries the kinetic energy of a flying mosquito, compressed into something trillions of times smaller. Yet despite this incredible achievement, they still fall short of true light speed. And if you want to know exactly what would happen if we could reach the speed of light, I cover that in my video called "What if we could reach the speed of light today?" If you are interested, the link is in the description and on the card above. The energy requirements are staggering. To accelerate just 1 kilogram of matter to 90% of light speed would require approximately 1.3 times 10 to the 17 joules, roughly the total energy consumption of the United States for several months. To reach 99% of light speed, you'd need about 6 times more energy. For 99.9%, 30 times more still. The curve is exponential, rising toward infinity as you approach the ultimate barrier. But mass-energy equivalence is only part of the challenge. Time dilation presents another bizarre obstacle. As Einstein discovered, time isn't absolute. It flows at different rates depending on your motion and gravitational environment. As you accelerate toward light speed, time literally slows down for you relative to the rest of the universe. At 90% light speed, time passes about half as fast. At 99.9%, time slows by a factor of 22. At speeds infinitesimally close to light speed, time nearly stops. This creates a paradox for light speed travel. From the perspective of a photon which travels at light speed, the journey from its point of emission to absorption takes zero time. Whether traveling across a room or across the universe, a photon experiences no passage of time. If humans could somehow reach light speed, we would experience instantaneous travel, but the universe would age infinitely during our journey. We'd arrive at the end of time itself. The particle physics experiments conducted over the past century have confirmed these relativistic effects thousands of times. Muons created in the upper atmosphere by cosmic ray collisions live only 2.2 microseconds at rest. They're created about 10 kilometers up and travel toward Earth at 99.9% light speed. Without time dilation, they should decay after traveling only 660 meters. Yet we detect them at Earth's surface because time dilation extends their lifetime from our perspective, allowing them to complete the journey. The Voyager 1 spacecraft, launched in 1977, represents humanity's most distant ambassador, now over 24 billion kilometers from Earth. Yet it's traveling at only 17 kilometers per second, about 0.0056% of light speed. At this rate, it would take over 73,000 years to reach Proxima Centauri, our nearest stellar neighbor, at 4.24 light-years away. Even our fastest spacecraft are essentially standing still on cosmic scales. The Parker Solar Probe, launched in 2018, holds the current speed record for a human-made object. During its closest approach to the Sun, it reaches speeds of about 192 kilometers per second, roughly 0.064% of light speed. This probe uses gravity assists from Venus and the Sun's own gravitational pull to achieve these velocities. But even this remarkable achievement is still 1,500 times slower than light. Current rocket technology faces fundamental limitations. Chemical rockets, like those that took us to the Moon, are limited by the energy stored in chemical bonds. The most efficient chemical reaction, hydrogen and oxygen combustion, releases about 13 megajoules per kilogram of fuel. This sounds impressive until you realize that accelerating that same kilogram to just 1% of light speed requires 45 trillion joules. You'd need more fuel than exists on Earth to reach even modest relativistic speeds. Ion drives, like those used on NASA's Dawn spacecraft, are far more efficient than chemical rockets. They accelerate charged particles using electromagnetic fields, achieving exhaust velocities 10 times higher than chemical rockets. The Dawn spacecraft's ion engine could theoretically accelerate the probe to 350,000 kilometers per hour, given enough time and fuel. But that's still only 0.03% of light speed. The fundamental problem remains: we're carrying our fuel with us, and the rocket equation shows that fuel requirements grow exponentially with desired velocity. Nuclear propulsion offers more promise. Project Orion, conceived in the 1950s, proposed using nuclear explosions to push a spacecraft. Theoretical designs suggested speeds up to 5% of light speed might be achievable. The spacecraft would drop nuclear bombs behind itself, riding the shockwaves on a massive pusher plate. The project was abandoned due to nuclear test ban treaties and the obvious environmental concerns of launching thousands of nuclear weapons into space. Fusion rockets, still in development, could theoretically achieve exhaust velocities of 3 to 5% light speed. The British Interplanetary Society's Project Daedalus, designed in the 1970s, envisioned an unmanned probe using deuterium-helium-3 fusion that could reach 12% of light speed. The theoretical Icarus design, updated in 2014, refined these concepts, but we haven't achieved controlled fusion for power generation on Earth, let alone in a spacecraft engine. Antimatter propulsion represents the theoretical pinnacle of reaction drives. When matter and antimatter annihilate, they convert 100% of their mass into energy, the maximum possible by Einstein's E equals mc squared. A spacecraft using matter-antimatter annihilation could theoretically achieve exhaust velocities near light speed, potentially accelerating a payload to 70% of light speed or higher. The problem? We can currently produce only nanograms of antimatter per year at a cost of trillions of dollars per gram. Storing it without it touching normal matter and annihilating is another enormous challenge. But even if we solved the propulsion problem, human biology presents perhaps insurmountable barriers. Acceleration itself becomes lethal at high levels. Fighter pilots experience 9 Gs, 9 times Earth's gravity, for brief periods using special suits and training. Sustained acceleration at even 3 Gs would be extremely uncomfortable. At 1 G of constant acceleration, equivalent to Earth's surface gravity, it would take about a year to approach light speed. This seems manageable until you consider the other effects. As you accelerate toward light speed, space itself transforms. The universe ahead of you appears compressed and blue-shifted, with light from stars shifting toward higher energies. Ultraviolet radiation becomes visible light, then X-rays, then gamma rays. The cosmic microwave background radiation, normally invisible, would blue shift into deadly radiation. At 99.9% light speed, this background radiation would hit you with the energy of deadly particle radiation. The faster you go, the more the universe itself becomes a lethal radiation field. Interstellar dust becomes another killer. Space isn't empty. It contains about 1 atom per cubic centimeter on average, plus larger dust grains. At low speeds, these are harmless. But at relativistic speeds, each grain of dust hits like a bomb. A dust grain weighing just 1 nanogram hitting your spacecraft at 99% light speed would impact with the energy of about 2 kilograms of TNT. The interstellar medium would become a continuous bombardment of high-energy particles and micrometeorites, requiring massive shielding that adds weight, which requires more fuel, which makes acceleration harder. The breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking and billionaire Yuri Milner, proposes a radical solution. Don't send humans at all and make the spacecraft incredibly tiny. The plan involves using powerful ground-based lasers to push tiny Starship spacecraft, weighing just grams, to 20% light speed. These nanocraft would carry cameras, communication equipment, and sensors on chips no bigger than a postage stamp. The physics works in principle. A 100 gigawatt laser array could accelerate these lightweight probes to relativistic speeds in minutes. They'd reach Proxima Centauri in about 20 years, sending back data that would take another 4.24 years to reach Earth. But the technical challenges are enormous, building lasers powerful enough, keeping them focused across interstellar distances, creating electronics that survive the acceleration and radiation, and communicating across light years with transmitters weighing grams. Recent calculations suggest the Bussard ramjet might not work at all. The drag from collecting interstellar hydrogen might exceed the thrust from fusing it, especially since interstellar space is emptier than Bussard assumed, containing about 1 atom per cubic centimeter rather than the 1,000 he hoped for. The fusion process would need to be far more efficient than anything we can currently achieve, and the electromagnetic scoop would require Superconducting magnets of unprecedented scale. Solar sails offer another propellantless propulsion method. These gossamer-thin reflective sheets use radiation pressure from stars to accelerate spacecraft. The Japanese Icaros mission proved the concept in 2010, successfully deploying a 14-meter solar sail. The Planetary Society's LightSail 2, launched in 2019, demonstrated controlled solar sailing in Earth orbit. But solar radiation pressure is incredibly weak, about 9 newtons per square kilometer near Earth. Reaching even 1% light speed would require sails hundreds of kilometers across, made of materials thinner than anything we can currently manufacture. The breakthrough Starshot concept combines solar sails with powerful lasers, solving the weak radiation pressure problem. By focusing gigawatt lasers on tiny light sails, the project aims to achieve the millions of Gs of acceleration needed to reach 20% light speed quickly. But this only works for gram-scale payloads. Scale up to human-carrying vessels, and the sail would need to be thousands of kilometers across, perfectly reflective, and able to withstand laser intensities that would vaporize any known material. Magnetic sails present an alternative to physical sails. By generating a large magnetic field around the spacecraft, you could deflect charged particles in the solar wind or interstellar medium, creating thrust. This avoids the material challenges of physical sails, but the magnetic fields required are enormous, potentially hundreds of kilometers across. Superconducting loops would need to carry currents of millions of amperes, requiring cooling systems and power supplies that add massive weight. Time dilation, often seen as a barrier, could actually be our ally for interstellar travel. At 99.999% light speed, 5 nines, time slows by a factor of 224. A journey to the Andromeda Galaxy, 2.5 million light-years away, would feel like only 11,000 years to the travelers. Still impossibly long, but if we could add more nines, the subjective time drops dramatically. At speeds infinitesimally close to light speed, travelers could cross the observable universe in what feels like a human lifetime. But reaching such speeds requires energy approaching infinity. Each additional 9 in that percentage requires roughly 10 times more energy than the previous one. The particle physics experiments that achieve these speeds work with individual protons or small bunches of particles. Scaling to macroscopic objects, let alone humans, enters the realm of impossibility with any conceivable technology. Cryogenic suspension or some form of suspended animation could make long journeys tolerable. If we could safely freeze humans or dramatically slow their metabolism, journey times of centuries become manageable. Current cryonics can preserve bodies after death, but no one has been successfully revived. The formation of ice crystals destroys cells, and we don't know how to prevent this damage or repair it afterward. Some organisms naturally survive freezing, suggesting solutions might exist, but applying this to humans remains science fiction. Digital consciousness uploading presents a radical alternative. If human consciousness could be transferred to computers, we could send digital humans at light speed as radio signals. The spacecraft would only need to carry equipment to receive the signal and construct new bodies, biological or robotic, at the destination. This sidesteps most physical limitations but requires technologies we can barely imagine: complete brain scanning, consciousness transfer, and artificial bodies indistinguishable from biological ones. Even if uploading becomes possible, questions remain. Is a digital copy really you, or just a copy that thinks it's you? Would the original person need to die for the copy to be genuine? These philosophical questions become practical concerns when considering consciousness as a means of space travel. The technology might arrive centuries before we resolve the ethical and philosophical implications. Quantum entanglement has been proposed for instantaneous communication or even teleportation across cosmic distances. Entangled particles remain correlated regardless of separation. Measuring one instantly affects the other. But this can't transmit information faster than light. The correlation is real, but you can't control what information appears. Quantum teleportation can transmit quantum states, but only by also sending classical information at light speed or slower. Physics seems carefully constructed to prevent faster-than-light information transfer. The M drive, proposed in 2001, claimed to produce thrust without propellant using microwaves in a closed cavity. Initial tests showed tiny thrust, raising hopes for propellantless propulsion. But subsequent rigorous testing found no thrust beyond experimental error. The device would have violated conservation of momentum if it worked, and most physicists were skeptical from the beginning. It joins a long list of proposed reactionless drives that don't survive careful testing. The limits of known physics paint a sobering picture. Every investigation reinforces the same conclusion. Light speed is a fundamental barrier built into space-time structure. Mass-energy equivalence makes acceleration increasingly difficult. Time dilation creates causality problems. Interstellar distances are vast beyond comprehension. The energy requirements exceed entire civilizations' capabilities. Yet humans have always pushed against the impossible, often succeeding where theory said we'd fail. Consider how our understanding has evolved. In 1903, the New York Times predicted human flight might be achieved in 1 to 10 million years. 66 years later, we walked on the moon. Lord Kelvin, one of the 19th century's greatest physicists, declared heavier-than-air flight impossible just 8 years before the Wright brothers' success. Arthur C. Clarke noted that when distinguished scientists call something impossible, they're very probably wrong. But relativistic physics differs fundamentally from engineering challenges. Flight was always physically possible. Birds demonstrated that. We just needed the right technology. Light speed isn't an engineering problem, but a feature of space-time itself. No amount of cleverness can overcome infinity. The energy required to reach light speed remains infinite regardless of technology. This isn't pessimism, but acknowledgement of physical law. Yet absolute light speed isn't necessary for interstellar exploration. At 10% light speed, achievable with fusion or antimatter propulsion, we could reach Proxima Centauri in 42 years. At 50% light speed, possible with efficient antimatter engines, the journey takes 8.5 years. From the traveler's perspective, time dilation reduces these durations slightly. While not the instant travel of science fiction, such speeds make interstellar colonization possible within human lifetimes. The economic argument for near-light speed travel is complex. The resources required, energy, materials, human talent, could transform civilization in other ways. Building the infrastructure for relativistic travel might cost quadrillions of dollars. That investment could instead eliminate poverty, reverse climate change, or build space habitats throughout the solar system. The opportunity cost of interstellar travel might be too high until humanity becomes vastly wealthier. Some argue we should focus on robotic exploration. Sending thousands of small, intelligent probes to nearby stars costs far less than one human mission. These probes could establish infrastructure, analyze planets, even begin terraforming before humans arrive centuries later on slower, safer ships. The first humans to another star might arrive to find cities already built by machines sent generations earlier. The Fermi paradox adds another dimension to this discussion. If faster-than-light travel were possible, even slightly, the galaxy should be teeming with interstellar civilizations. A species with FTL technology could colonize the entire Milky Way in just millions of years, an eye blink in cosmic time. Yet we see no evidence of galaxy-spanning civilizations. Either we're among the first intelligent species they're hiding, they self-destruct, or, most relevant here, Practical interstellar travel is so difficult that few civilizations achieve it. The simulation hypothesis offers a weird loophole. If our universe is a simulation, the light speed limit might be artificial, a programming constraint to reduce computational requirements or prevent simulated beings from escaping. In this scenario, sufficiently advanced technology might hack reality's operating system, modifying or bypassing the speed limit. This is pure speculation, but it illustrates how desperate we are for solutions that physics seems to forbid. More grounded possibilities exist within known physics. Gravitational slingshots around black holes could accelerate spacecraft to tremendous speeds. A close approach to a rotating black hole's ergosphere, the region where space-time itself is dragged around, could extract energy from the black hole's rotation. In principle, this Penrose process could accelerate spacecraft to significant fractions of light speed using the black hole's own energy. But reaching a black hole presents its own challenge. The nearest known black hole is about 1,000 light-years away. We'd need near light speed travel to reach it in reasonable time, creating a circular problem. Plus, the radiation environment near black holes is lethal, and tiny navigation errors would be fatal. It's a solution that requires solving the problem first. Technological advancement often follows exponential curves. Computing power doubles every 2 years. Genetic sequencing costs drop by half annually. If propulsion technology improved exponentially, when might we reach significant fractions of light speed? Unfortunately, propulsion hasn't followed this pattern. Chemical rocket efficiency improved marginally since the 1960s. Ion drives are only slightly better than early designs. We're hitting physical limits, not just engineering challenges. Breakthrough physics might change everything. Before Einstein, light speed wasn't known as a universal limit. Before quantum mechanics, the microscopic world seemed deterministic. Perhaps future discoveries will reveal loopholes or entirely new physics. String theory's extra dimensions, quantum gravity's structure, or dark energy's nature might offer possibilities we can't imagine. But hoping for new physics to save us is essentially hoping for magic. The social implications of sublight interstellar travel deserve consideration. If journeys take generations, entire cultures would evolve in space. Languages might diverge. Religions could form around the journey itself. Children born in interstellar space might reject their parents' mission. The first generation chose to leave Earth. Their descendants had no choice. The ethical implications are staggering. Do we have the right to commit unborn generations to life in a tin can between the stars? Communication delays compound these issues. Messages to Earth take years, then decades, then centuries as the ship travels farther. Eventually, communication becomes impossible, not technically but practically. Who sends messages knowing the reply won't arrive for centuries? Interstellar colonies would be truly independent, perhaps developing into separate human species over time. We wouldn't be expanding human civilization so much as seeding new ones. The biological challenges of long-term space travel remain largely unsolved. We know that zero gravity causes bone loss, muscle atrophy, and cardiovascular problems. Cosmic radiation damages DNA, increasing cancer risk and potentially causing cognitive decline. Years of research on the International Space Station have shown these effects, but ISS astronauts are still protected by Earth's magnetosphere and can return home after months. Interstellar travelers would face decades or centuries of exposure with no possibility of return. Artificial gravity through rotation could solve some problems, but creating Earth-like gravity requires either massive rotating structures or high rotation rates that cause disorienting Coriolis effects. A rotating habitat with a 100-meter radius would need to spin at about 3 revolutions per minute for Earth gravity, slow enough to be tolerable. But such structures would weigh thousands of tons, multiplying the energy needed for acceleration. Radiation shielding presents another mass penalty. Cosmic rays are high-energy particles that can penetrate meters of shielding. The atmosphere above us equals 10 tons per square meter of shielding, and Earth's magnetic field deflects many particles. Duplicating this protection in space would require massive shields or powerful magnetic fields, both adding enormous weight. Some propose using the spacecraft's fuel or water supplies as shielding, but even this multi-use approach adds significant mass. The closed ecosystem problem has never been fully solved. Biosphere 2, the 1990s experiment in creating a sealed, self-sustaining environment, failed within 2 years. Oxygen levels dropped, carbon dioxide spiked, and many species went extinct. The participants needed outside food supplies. If we can't maintain a closed ecosystem on Earth with unlimited initial resources and emergency backup, how can we maintain one in space for centuries? Recent advances offer some hope. 3D printing could allow spacecraft to manufacture replacement parts from raw materials, reducing the need to carry spares. Genetic engineering might create crops optimized for spacecraft conditions or bacteria that recycle waste more efficiently. Artificial intelligence could manage complex life support systems and diagnose problems before they become critical. But these technologies remain largely theoretical for the demanding environment of interstellar space. The psychological challenges might be insurmountable. Humans evolved in wide open spaces with changing seasons, weather, and diverse ecosystems. Confining people to spacecraft for decades would likely cause severe psychological stress. Antarctic research stations, nuclear submarines, and Mars simulation experiments show that even motivated volunteers develop conflicts, depression, and cognitive issues after months in isolation. Scale this to lifetimes, and the problems multiply. Virtual reality might provide psychological relief, offering simulated environments and experiences. But would virtual nature satisfy our evolutionary needs? Would people living their entire lives in virtual worlds remain motivated to maintain the real spacecraft? The risk of entire populations retreating into virtual fantasies while their life support systems decay is real. We might arrive at distant stars only to find ships full of people who no longer care about the physical world. Some propose that humans themselves need modification for interstellar travel. Genetic engineering could create radiation-resistant humans able to hibernate for decades or thriving in low gravity. More radically, we might merge with machines, becoming cyborgs immune to radiation and capable of surviving in vacuum. But such modifications raise questions about whether the beings arriving at distant stars would still be human in any meaningful sense. The discovery of thousands of exoplanets has revealed that planetary systems are common, but Earth-like worlds are rare. Most planets are too hot, too cold, lack atmospheres, or orbit unstable stars. Even seemingly perfect candidates might have deal-breakers we can't detect from Earth: toxic atmospheres, extreme weather, or aggressive microorganisms. Terraform these worlds might take millennia. Interstellar colonists might spend generations transforming hostile worlds while living in domes or underground. This raises the question, why leave the solar system at all? Mars, the Moon, asteroids, and space habitats could house trillions of humans. The solar system contains enough resources for millions of years of growth. By the time we need more space, we might have technologies that make interstellar travel trivial or unnecessary. The urgency driving science fiction's interstellar imperative doesn't exist in reality, unless Earth faces existential threats. Asteroid impacts, nuclear war, climate catastrophe, or pandemics could destroy civilization. Establishing self-sufficient colonies elsewhere provides insurance against extinction. But Mars or lunar colonies would suffice for most scenarios. Only threats to the entire solar system, a nearby supernova, gamma-ray burst, or the sun's eventual death require interstellar colonization. The Sun will remain stable for another 5 billion years, gradually warming but supporting Earth-like conditions for at least another billion years. That's more time than complex life has existed on Earth. On such timescales, assuming humanity survives, our descendants might be as different from us as we are from bacteria. They might upload consciousness to computers, exist as pure energy, or transcend physical reality entirely. Planning interstellar travel for beings we can't imagine seems presumptuous. Near-term possibilities remain exciting. SpaceX aims to reduce launch costs through reusability, making space more accessible. Blue Origin, Virgin Galactic, and dozens of startups are commercializing space. Nuclear propulsion, banned from development during the Cold War, is being reconsidered for Mars missions. Fusion rocket research continues at Princeton, NASA, and private companies. These incremental advances might eventually compound into breakthrough capabilities. The James Webb Space Telescope, operational since 2022, is revolutionizing our understanding of exoplanets. By analyzing light passing through their atmospheres, we can detect water, methane, oxygen, and other molecules. We're finding that planets are incredibly diverse: hot Jupiters orbiting closer than Mercury, super-Earths with no solar system analog, and water worlds covered in global oceans. Each discovery refines our targets for eventual interstellar missions. SETI, the search for extraterrestrial intelligence, adds another dimension. If we detect signals from an advanced civilization, the motivation for interstellar travel changes entirely. Contact with aliens, even just radio communication, would provide technological insights, cultural exchange, and answers to humanity's deepest questions. The knowledge that intelligence exists elsewhere might inspire the massive investments needed for interstellar travel, but SETI has found only silence so far. After decades of searching, we've detected no artificial signals, no megastructures, no obvious signs of intelligence. This great silence might mean life is rare, intelligence rarer still, or that advanced civilizations don't broadcast signals we can detect. It might also mean that the light-speed barrier truly is insurmountable, keeping civilizations isolated in their stellar neighborhoods forever. The technological singularity, the hypothetical point when artificial intelligence surpasses human intelligence, could change everything. A super-intelligent AI might solve physics problems we can't comprehend, design propulsion systems we can't imagine, or find loopholes in laws we think are absolute. Or it might calculate that interstellar travel is pointless, that virtual worlds are superior to physical exploration, or that humanity should remain on Earth. Some physicists speculate about phase transitions in the vacuum of space. Just as water suddenly becomes ice at 0 degrees Celsius, space itself might undergo phase transitions under extreme conditions. If we could trigger such transitions, perhaps we could modify spacetime's properties locally, reducing the effective speed of light limit or creating regions where different physics applies. This is highly speculative, but it illustrates that our understanding of physics remains incomplete. Dark energy, discovered in 1998, accelerates the universe's expansion. We don't know what it is, only that it comprises 68% of the universe's energy density. If we could harness dark energy, we might have access to vast power sources. Some theories suggest dark energy's strength varies over time or space. Understanding and manipulating it could provide the energy needed for relativistic travel. Dark matter, comprising 27% of the universe, remains equally mysterious. It doesn't interact electromagnetically, making it invisible, but its gravitational effects are obvious. Some theories propose dark matter consists of particles we could potentially detect and manipulate. If dark matter interacts through forces beyond gravity, it might enable technologies we can't currently conceive. Quantum mechanics might offer unexpected possibilities. Quantum tunneling allows particles to pass through barriers they classically couldn't overcome. Scaled up enormously, could spacecraft tunnel through space-time itself? Quantum superposition allows particles to exist in multiple states simultaneously. Could macroscopic objects, even spacecraft, exploit superposition for travel? These ideas are fantastically speculative, but quantum mechanics has surprised us before. The many-worlds interpretation of quantum mechanics suggests every quantum event creates parallel universes. If true, perhaps we could travel between parallel worlds where distances are different, or physics allows faster-than-light travel. This enters the realm of pure speculation, but it shows how desperate we are for solutions to the light-speed barrier. More practically, the combination of multiple technologies might achieve what single approaches cannot. Solar sails accelerated by lasers could reach 5% light speed. Once at speed, Bussard ramjets might maintain velocity using interstellar hydrogen. Magnetic sails could provide deceleration at the destination. Fusion rockets could maneuver within the target system. Each technology handles the phase where it's most efficient. The economics of interstellar travel might improve through resource utilization. Asteroid mining could provide materials for spacecraft construction in space, avoiding Earth's gravity well. Helium-3 from the Moon or gas giants could fuel fusion rockets. Self-replicating robots could build infrastructure throughout the solar system, creating an industrial base for interstellar missions. The first Starship might be built entirely from space resources. International cooperation could pool resources and knowledge. The International Space Station proves that former enemies can collaborate in space. An interstellar mission taking centuries and benefiting all humanity might unite nations in common purpose. The technological developments would have immediate benefits: fusion power, closed ecosystems, artificial intelligence, life extension, justifying the investment even if the mission ultimately fails. Private initiatives might succeed where governments hesitate. SpaceX reached orbit faster and cheaper than expected. Breakthrough Starshot attracted private funding for interstellar research. Billionaires like Elon Musk and Jeff Bezos openly discuss multiplanetary civilization. As private wealth grows and technology advances, a coalition of wealthy individuals might fund humanity's first starship. The cultural impact of attempting interstellar travel, regardless of success, could be transformative. The Apollo program inspired a generation of scientists and engineers. An interstellar program would require centuries of sustained effort, creating a long-term perspective currently lacking in human civilization. Working toward a goal beyond individual lifetimes might help humanity mature as a species. Educational benefits alone could justify the effort. Students learning physics, engineering, biology, and other fields would have a concrete goal, contributing to humanity's greatest adventure. Research into life support systems would advance medicine and agriculture. Propulsion research would develop new energy sources. The psychological studies of isolated communities would help us understand human nature. Every aspect of an interstellar program would push the boundaries of human knowledge. The philosophical implications run deep. Attempting interstellar travel forces us to confront our mortality, not just as individuals, but as a species and planet. We must think beyond electoral cycles, quarterly profits, and individual lifespans. We must consider what humanity should become, not just what we are. These questions, prompted by the practical challenges of crossing interstellar distances, could spark a renaissance in human thought. Consider what we've learned about Mars through robotic exploration. The Curiosity and Perseverance rovers have revealed an ancient world that once had rivers, lakes, and possibly oceans. Organic molecules exist in Martian rocks. Methane appears seasonally in the atmosphere. Each discovery raises questions that only human explorers can fully answer. The same will be true for exoplanets. Robots can survey, but humans must explore to truly understand. The timeline for developing interstellar capability might span centuries. Fusion power might arrive by 2050. Antimatter production could become practical by 2100. Closed ecosystems might be perfected by 2150. Each breakthrough enables the next. By 2300, combining these technologies might make 10% light speed achievable. By 2500, 50% might be possible. These timescales seem vast to individuals but are eye blinks in cosmic time. Climate change adds urgency to space development. As Earth's resources strain under billions of humans, space offers unlimited energy from the sun, raw materials from asteroids, and living space in artificial habitats. Developing these resources requires many technologies needed for interstellar travel: closed ecosystems, fusion power, advanced robotics. Saving Earth might give us the tools to leave it. Artificial general intelligence might arrive this century, transforming every aspect of interstellar travel. AI could design optimal spacecraft, solve closed ecosystem problems, and maintain equipment for centuries. More importantly, AI might be the ideal interstellar explorer, immune to radiation, capable of hibernation, and able to duplicate itself at the destination. Humans might follow paths blazed by artificial minds. The ethical framework for interstellar travel needs development. Who decides whether humanity should attempt such journeys? How do we obtain consent from future generations who will live and die aboard starships? What rights do colonists have to terraform worlds that might harbor primitive life? These questions have no easy answers, but discussing them prepares us for decisions our descendants will face. Life extension technology could make personal interstellar travel feasible. If humans routinely live 200 years or more, a 40-year journey becomes a smaller fraction of life. Suspended animation or dramatic metabolic slowdown could make subjective travel times even shorter. The same technologies that conquer aging might conquer the distances between stars. The discovery of life elsewhere would change everything. Finding microbes on Mars or in Europa's ocean would suggest life is common. Detecting atmospheric biosignatures on exoplanets would confirm it. Knowing that life exists throughout the galaxy would make interstellar travel feel less like abandoning Earth and more like joining a living universe. The philosophical shift could provide motivation that mere curiosity cannot. Quantum computers might reveal new physics. By simulating quantum systems impossible to study directly, we might discover phenomena that current theories miss. Perhaps space-time has exploitable properties at quantum scales. Perhaps information theory holds keys to transcending physical limitations. Each advance in fundamental physics opens new possibilities. The sustainability movement teaches long-term thinking, building a civilization that lasts millennia on Earth, using renewable energy, recycling everything, living within planetary boundaries, develops skills essential for interstellar travel. A starship is the ultimate sustainability challenge, a closed system that must function perfectly for centuries. Earth is our training ground for the stars. Space tourism is creating infrastructure and public interest. As costs drop and safety improves, millions might experience space firsthand. Orbital hotels, lunar bases, and Mars colonies will follow. Each step makes the next easier. By the time we attempt interstellar travel, living in space might be routine for millions of humans. The extraordinary becomes ordinary through repetition. Risk assessment for interstellar travel differs from anything in human experience. The probability of catastrophic failure is high, but the potential reward, ensuring humanity's survival and spreading consciousness through the cosmos, is immeasurable. How do we weigh certain costs against speculative benefits? How much should the present sacrifice for a future that might never arrive? The anthropic principle suggests we exist because the universe's physical constants allow our existence. In universes with different light speeds, matter might not form, stars might not shine, or life might be impossible. The light speed limit that frustrates our ambitions might be essential for our existence. Perhaps the barrier that keeps us confined also keeps us alive. Looking at the vastness of cosmic time changes our perspective. The universe is 13.8 billion years old. Earth formed 4.5 billion years ago. Complex life emerged perhaps 600 million years ago. Humans have existed for 300,000 years, civilization for 10,000, and the space age began just 65 years ago. If we survive another million years, a trivial span cosmically, technology might advance beyond recognition. Patience, not speed, might be the key to the stars. The concept of a galactic civilization requires rethinking human identity. If colonies around different stars evolve separately for thousands of years, they might become distinct species. Genetic drift, adaptation to local conditions, and deliberate modification could create beings as different from each other as we are from Neanderthals. Would this be humanity spreading through the galaxy, or humanity fragmenting into something else entirely? Recent discoveries in neuroscience suggest consciousness might be more flexible than we think. If we understand how brains create subjective experience, we might transfer consciousness between substrates, biological brains, silicon chips, quantum computers, or exotic structures we can't imagine. A consciousness that can move between bodies might experience interstellar travel differently. The journey could feel instantaneous if you're turned off at departure and reactivated at arrival. The simulation hypothesis raises profound questions about the nature of distance itself. If our universe is computed, then the vast distances between stars might be compression algorithms, ways to reduce computational load by making most of the universe inaccessible. In this view, the light speed limit isn't a physical law but a design choice. Breaking it would require hacking reality itself, assuming that's even possible within the simulation. Consider the energy hierarchy of civilizations. The Kardashev scale classifies civilizations by energy use. Type 1 harnesses all energy reaching their planet from its star. Type 2 harnesses their star's entire output. Type 3 harnesses their galaxy's energy. Humanity currently rates about 0.73. Reaching even Type 1 might take centuries. But a Type 2 civilization building Dyson spheres around stars would have energy budgets making interstellar travel trivial. The Drake equation estimates the number of communicating civilizations in our galaxy. Depending on the values chosen, estimates range from 1s to millions. If millions of civilizations exist, why haven't we detected them? The light speed barrier might be the answer. Perhaps every civilization discovers the same limit and remains confined to their stellar neighborhood. The galaxy might teem with isolated islands of intelligence forever separated by physics. Panspermia, the idea that life spreads between worlds, offers a different perspective. Microbes might survive in rocks blasted from planets by asteroid impacts, drifting between stars for millions of years before landing somewhere hospitable. Life might naturally cross interstellar distances just very slowly. Humans attempting to travel between stars in decades might be missing the point. Perhaps the natural timescale is millions of years and patience is mandatory. The concept of universal computation suggests that sufficiently advanced technology becomes indistinguishable from nature itself. Perhaps mature civilizations don't build starships but engineer stellar systems, moving stars themselves rather than traveling between them. A civilization that can harness stellar energy might find it easier to bring stars together than to cross the distances between them. What looks like natural stellar motion might be cosmic engineering. Black hole farming could provide ultimate energy sources. A civilization could feed matter into artificial black holes, extracting energy from the accretion process with near-perfect efficiency. These black holes could power spacecraft, provide artificial gravity, and serve as ultimate waste disposal. A black hole starship feeding on interstellar matter might achieve velocities impossible for conventional rockets. The engineering challenges are stupendous, but physics allows it. The role of information theory in physics continues growing. Some physicists suspect information, not matter or energy, is the universe's fundamental component. If true, distance might be redefinable in information theoretic terms. Quantum entanglement already shows that information relationships ignore classical distance. A deeper understanding might reveal that spatial separation is less fundamental than it appears. Consider what we're really seeking with faster-than-light travel. Is it exploration, communication, resource acquisition, escape from existential threats? Each goal might have solutions that don't require breaking physics. Virtual reality could provide unlimited exploration. Quantum communication might enable instant messaging without traveling. Fusion power and asteroid mining could provide unlimited resources. Spreading through the solar system could ensure survival. Perhaps we're fixating on speed when we should focus on achieving our actual goals. The possibility of mind uploading creates scenarios where consciousness travels at light speed as radio signals. A civilization of uploaded minds could explore the galaxy without moving any mass. They could pause their consciousness during transmission, experiencing instantaneous travel. They could duplicate themselves, sending copies to multiple stars simultaneously. Death becomes meaningless if you can restore from backup. The challenges shift from physics to philosophy. Are you still you after being transmitted across space? Metamaterials with exotic properties hint at possibilities beyond current engineering. Materials with negative refractive index, programmable matter that changes properties on command, and structures that manipulate spacetime at microscopic scales might enable technologies we can't foresee. Just as semiconductors enabled computers unimaginable to their discoverers, tomorrow's materials might enable propulsion systems beyond current conception. The expansion of the universe adds a temporal barrier to the spatial one. Distant galaxies recede from us, carried by expanding space. Galaxies beyond certain distances move away faster than light, not through space, but with space. We can never reach them, no matter our technology. Each moment, more of the universe crosses this horizon, becoming forever inaccessible. If we delay too long, even nearby galaxies might slip beyond reach. The universe itself imposes a deadline on interstellar ambitions. Reflecting on everything we've explored, a pattern emerges. Every angle of attack on the light-speed barrier, from brute force acceleration to exotic physics, from generation ships to consciousness uploading, runs into fundamental limits. It's not one barrier, but many. Energy requirements approaching infinity, time dilation preventing meaningful travel, biological fragility, technological inadequacy, and the sheer hostility of interstellar space. The universe seems designed to keep civilizations local, separated by gulfs of space and time that dwarf human comprehension. Yet this isn't cause for despair, but for wonder. The same physics that traps us in our cosmic neighborhood enables our existence. If light had no speed limit, causality would break down and the universe would be chaos. If mass-energy equivalents didn't exist, stars couldn't shine and heavy elements couldn't form. The barriers to interstellar travel are the same laws that allow atoms, chemistry, biology, and consciousness to exist. We're not imprisoned by arbitrary restrictions, but protected by the fundamental architecture of reality. Consider how far we've come in understanding these limits. A century ago, we didn't know other galaxies existed. We thought the Milky Way was the entire universe. We had no concept of space-time, no understanding of why stars shine, no idea that the universe was expanding. In one human lifetime, we've mapped billions of galaxies, detected gravitational waves, discovered thousands of planets. and pushed the boundaries of space exploration from wooden biplanes to the edge of the solar system. This progression suggests humility about what we think is impossible. Yes, current physics says reaching light speed requires infinite energy, but current physics is incomplete. We don't understand dark matter, dark energy, quantum gravity, or consciousness itself. Each breakthrough reveals new mysteries. Perhaps some future Einstein will discover that our universe is far stranger than we imagine, with possibilities we can't conceive. Not magic or wishful thinking, but genuine discoveries about reality's nature. Even without breaking the light speed barrier, the future of human space exploration inspires awe. Mars colonies in this century, asteroid mining providing unlimited resources, fusion rockets opening the outer solar system, space habitats housing millions in perfect environments, telescope arrays detecting signs of life around distant stars. Each achievement builds toward a spacefaring civilization that, while not traveling faster than light, expands human presence throughout the solar system and eventually to nearby stars. The journey to even 10% light speed would transform humanity. The technologies required, closed ecosystems, fusion power, artificial intelligence, life extension, radiation shielding, would revolutionize life on Earth. The social changes, long-term thinking, global cooperation, investment in pure science would mark humanity's maturation as a species. Even if we never leave the solar system, attempting interstellar travel would spark advances benefiting billions. Perhaps the real question isn't whether humans will reach light speed, but whether we'll transcend the need for it. Virtual worlds might become indistinguishable from reality, offering infinite experiences without physical travel. Uploaded consciousness might explore computational universes vaster than physical space. Artificial intelligence might satisfy our curiosity about the universe without biological humans traveling anywhere. The future might be stranger than star-traveling humans. It might be post-human entirely. But something in the human spirit rebels against these limitations. We're the species that crossed oceans on wooden rafts, that climbed mountains because they were there, that sent robots to Mars and probes beyond the solar system. The same drive that carried us from Africa to every continent, from the ground to the moon, calls us to the stars. Even if physics says we can't travel faster than light, we'll push against that barrier with everything we have. The cosmic perspective reminds us that we're part of something magnificent. Every atom in your body except hydrogen formed in stellar cores, the carbon in your DNA, the oxygen you breathe, the iron in your blood, all were forged in stars that lived and died before our sun was born. We're literally made of star stuff, as Carl Sagan said. The universe has evolved the capacity to understand itself through us. We're not separate from the cosmos, but expressions of it, momentary patterns of matter and energy that gain the ability to wonder about our origins and destiny. Whether or not we physically reach the stars, we're already connected to them. The light entering your eye from distant stars left them years, centuries, or millennia ago. You're in direct physical contact with the universe through photons that traveled across space to reach you. When you look at the night sky, you're not just observing the universe, you're participating in it, completing the journey of light that began in distant stellar atmospheres. The question of reaching light speed ultimately reflects our deepest aspirations and fears, the aspiration to explore, to grow beyond our boundaries, to ensure our survival, to satisfy our curiosity about what lies beyond the horizon, the fear of being forever trapped, of cosmic loneliness, of missing out on the universe's wonders, of being a fleeting phenomenon in an uncaring cosmos. These emotions drive us to imagine breaking physical laws that seem absolute. But perhaps the journey matters more than the destination. The attempt to reach the stars, even at subliminal speeds, would unite humanity in common purpose. It would require us to think beyond individual lives, beyond nations, beyond short-term gains. It would challenge us to become more than we are, more patient, more cooperative, more far-sighted. The star travelers might not be us, but what we become through attempting the impossible. As we stand at the shore of the cosmic ocean, we're like our ancestors who first saw the sea and wondered what lay beyond the horizon. They couldn't imagine the continents awaiting discovery, the technologies that would carry them there, or how the journey would transform them. We can't imagine what awaits among the stars or how attempting to reach them will change us. But just as they set sail into the unknown, we'll find ways to cross the void, even if we can't break the ultimate speed limit. The light speed barrier stands as both humanity's greatest challenge and most profound teacher. It forces us to confront our limitations while inspiring us to transcend them. It reminds us that the universe operates by laws we didn't write and can't break, yet challenges us to work within those laws to achieve the impossible. It may forever prevent us from sailing between stars as easily as we fly between cities, but it cannot prevent us from trying, from learning, and from becoming more than we were. If you made this far, please make sure to subscribe and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. What if the speed of light changed? Discover how even a tiny change in light speed would completely rewrite the laws of physics and reshape the entire cosmos. See you there.